Hello everyone, I'm Charlotte and this is the chemistry of coffee. So to start it off, what is coffee? So basically coffee is a drink that over 80% of people in America drink every day. And people drink it because it makes you less tired in the mornings, and knowing everybody, sleep is rare. And you're tired because you have to wake up early and go to school or your job or whatever the heck you have to do. The reason that I wanted to study coffee is because I drink it every morning. I'm very addicted, and I wanted to see what's actually going on inside of my brain when I drink this thing. And I know a lot of other people probably want to know this too. So here's my gift to you if you drink coffee. The molecule inside of coffee that I studied was caffeine. And caffeine is a stimulant, makes you less tired, and it's also present in like a lot of other foods and drinks, but we're focusing on coffee today because that's what my project is about. The equation for caffeine is C8, which means there's 8 carbon atoms, H10, which means there's 10 hydrogen atoms, N4, which means there's 4 nitrogen atoms, and O2, which means there are 2 oxygen atoms, which probably could have guessed. But the molecular weight of coffee is 194.2 grams per mole. Alright, now to the history of coffee. Coffee came Southern Central America and Africa. Like, those are the 2 main places where coffee is harvested from. And it is theorized that coffee either came from Ethiopia or Egypt, because that's where most of the legends are from. One funny story of how it was created is there was a farmer who had goats in Ethiopia. And one day, the goats started eating these weird berries and they got really hyper. So of course, farmer, being farmer, was like, I wonder what these things are. So people ate the berries, they became hyper too. That's how coffee originated. But at first people would just soak the berries in hot water and then drink that. But eventually they learned how to dry the beans and make coffee that we drink today. In the 17th century, coffee made its way to Europe, and Europe, being good at spreading things like smallpox, spread it all over the world. That's how coffee came to be. So this is kind of the important part. Basically, caffeine is a molecule, and inside of your brain there are different receptors that connect to different molecules and basically change the way you work and you act and you feel. The caffeine, when you drink it or ingest it, it makes its way to your adenosine receptors, and your adenosine receptors obviously connect with adenosine. It naturally occurs in your brain and makes you tired and sleepy, so it's the complete opposite of caffeine. But molecularly, they look pretty similar. Caffeine is able to trick your adenosine receptors into thinking that oh, I'm adenosine, but it isn't. So once it attaches to the receptors, they can't expel it, so caffeine just completely takes over. It gives you an adrenaline rush, makes your heart beat faster, and kind of puts your body into flight or fight response. This only lasts for a couple hours, and when those couple hours are over and the caffeine's left your body, you get really tired, even more tired than you were to begin with. This is what makes it really addictive, because your body becomes dependent on that rush, and if you don't have it every day, you can get headaches, you can get stomach aches, and you just don't feel good. Now we're going to look at the structure of caffeine. So here's me and my molecule that I made. It's very nice. So basically the first thing that we're going to be talking about is our Lewis dot structure. So every atom has a different amount of valence electrons, which is basically the outer shell of the atom. And in order for it to become happy, it needs to have 8. It's the octet rule. But there are a couple things, like hydrogen, for instance, which only needs 2 valence electrons to become happy. You can see all the different electrons. So nitrogen has 2 left over, oxygen has 4, so on and so on. But carbon is special because of the 4 valence electrons it has. It makes 4 bonds, and then it is happy. It will always bond to something, and usually that something is hydrogen. Lines mean that there's 2 electrons shared, and then each dot is just 1 electron, and then these 2 lines mean that there are 4 electrons shared. Carbon will attach to hydrogen with its leftover molecules, so they're usually together. And then my next one is my skeletal structure. I'm sorry, I'm not good with computers. I couldn't figure out how to turn it around. But basically, here, let me just do this for you. It's very similar to the Lewis dot structure, but you probably noticed that, hey, there's no carbon. And the reason for that is because each of these points is where a carbon would be. And usually there's a ton of carbon in most molecules. So people are just like, pshaw, I don't want to do that because scientists are lazy. So they just pretend like they're there. And as I said, each of these things still means that there's 2 electrons shared. But since this is not the Lewis dot structure, you don't have to do the extra little like dots around it. And then finally, my 3D model that I made using marshmallows and pasta. I hope you enjoy it because it took a buttload of time. But thank you for watching, and I hope you learned something.